Hi everyone. I decided to create this video as a supplement to Chapter 10, Modeling Relationships, because the book covers very quickly the topic of multicollinearity. If you look at page 220 of the textbook, the last bullet point is about multicollinearity, and the book talks about it when you are interpreting the multiple linear regression output. And the multicollinearity piece is an important one. The book has just a paragraph to talk about it, but I decided to create a little more detailed presentation about it because it's an important factor that we have to deal with quite a bit when we conduct nutrition studies and we do analysis in studies that include dietary variables. So what is the definition of multicollinearity? It's a situation where two or more variables are very closely linearly related. You can look at this as there is a strong correlation between two or more variables, and we know how to do this, how to look at a correlation between two variables from chapter 9. You can run a Pearson's correlation if the two variables are continuous. And this way you can tell if there is a strong correlation between two variables or not. So there's also the concept of perfect collinearity, which is when your predictors are very, very closely related. So when that correlation coefficient is approaching 1 or is equal to 1. Perfect collinearity is when the correlation coefficient is actually 1. And the problem is that if there is a perfect collinearity between predictors, it is really not possible to obtain a unique estimate of the regression coefficients. And why is that? That's because there is an numerous number of combinations of coefficients that would work equally well. And in other words, the values of betas, or your correlation coefficient, your regression coefficients, are interchangeable for each one of your variables. So now you cannot tell anymore which variable contributes what. And we really need to worry about collinearity when there are high levels of collinearity. If you have low levels of collinearity, that poses little threat to the model estimates. But as collinearity increases, there are three problems that we need to worry about. The first one is that you get untrustworthy betas. So as collinearity increases, so do the standard errors of your beta coefficients from your regression model. And that means that you have more variability in your betas across samples. So this is a problem because now it probably means that your model really does not agree with what you see in the population, or it's not a good representation. I guess that's the better term of your population of interest. Second problem is that high collinearity limits the size of your R, or your R squared. When there is collinearity and you add a second variable to the model, now that variable is not really going to account for a unique variance. In other words, both variables account for the same variance, which brings me to the third problem, which is the importance of the predictors. Now you cannot tell anymore which predictor is more important in your model. So these issues are important issues when you're trying to build a predictive model, and you don't want to include too many terms that are very correlated with each other, because now they may be contributing the same variance, and that's not the purpose of a regression analysis. So how do we identify multicollinearity? The book doesn't talk much about this, but this is important. So there are a couple of different ways you can do that. You can just take a look at the the correlation coefficients and see if they are high, like in 0.8 or 0.9, that means that your predictor variables are highly correlated with each other and that you're going to have a problem with multicollinearity. But there's a more objective way to do this using SPSS, and that's to compute the variance inflation factor, or VIF. And the tolerance statistic is calculated from the VIF by just doing the reciprocal of VIF, 1 over VIF. So once you calculate those, if you have large VIFs, like greater than 10, or if your tolerance is below 0.1, this indicates a serious problem with collinearity or multicollinearity. If your average VIF is substantially greater than 1 but maybe below 10, then there may be a bias in your regression coefficients. And if your tolerance is below 0.2 but above 0.1, then that also may indicate a potential problem with multicollinearity. So these are objective ways for you to look at it. Now, how do we deal with multicollinearity? One strategy that a lot of people use is to eliminate the variables that are highly correlated with each other from the model and maybe keep only one of the variables. And the problem with this is that how will you know which variable to keep, right? So usually you want to include in your models variables that are not really correlated with each other. They are not telling the similar story. And I mean, in a way, you may be able to do this just by knowing the nature of some of your variables. We know, for example, in nutrition with diet, we know that calories from your diet is highly correlated with the amount of fat that you consume. So when you are building a model that includes diet factors as predictors, you may not be able to include both fat and calories. And I'll show you an example in a bit here. So some statisticians actually suggest that for each variable that you are removing based on that high correlation, you add another variable to your model so you do not end up with a model that is too simplistic. The truth is there is not a good answer for this, but you definitely need to deal with this issue. If you have variables that are highly correlated, you probably just want to include one of them. I just wanted to show you here my source for some of this additional content for the course is a book by Andy Field called Discovering Statistics Using IBM SPSS Statistics. And that book is just very overwhelming because it has a lot of stuff, but it really helps to explain concepts a little better.